Hello, this video shows how to improve the EVM when using an Analog Devices AD9081 MxFE chip by using equalization. This is the second video that we're doing on this subject. A previous YouTube video is the AD9082 EVM Improvement using equalization. I would encourage you to go take a look at that video because we do a brief discussion of equalization. We talk about why equalization is necessary, and then we give a live demo using an 8 PSK waveform, a 64 APSK waveform, and a 256 QAM waveform. We're not going to repeat the subject matter from that one in this video, so there's some good things there that might be helpful to you in understanding the subject matter. In this video, we're going to switch things up and use the AD9081 chip, a very similar chip to the 9082, just a little bit different. We're going to demonstrate what we're calling arbitrary waveform equalization. And we will use a non-communications type of waveform to determine the equalization. In this video, we'll show you first of all the measurement setup that we'll be using, and then we'll jump right into a demo of arbitrary waveform equalization. We're going to be using a chirp waveform, and we'll show it first of all without equalization, then with some adaptive equalization, and then with some fixed equalization. And then finally we'll get to showing the effects on EVM for communication signals when we use this arbitrary waveform equalization to set up fixed equalization. And then we'll have a conclusion. Here's the measurement setup that we'll be using. The green board is a Xilinx AMD ZCU102 host board that's running Analog Devices IIO software. The little blue board is an Analog Devices AD9081 FMCA EBZ eval board. The DACs on that board are 16-bit, 12 gigasample per second, and the input data rate is going to be 250 megasamples per second. On the ADC side, we've got 12-bit, 4 gigasample per second, and the output rate is 250 megasamples per second. We've got DAC 0 looped back to ADC 0 using an SMA cable. For a signal, we're going to use a 200 megahertz chirp with a 40 microsecond duration and a 50% duty cycle. You'll see that when we get to running the software. Just want to make a note that 200 megahertz is the total usable bandwidth at this data rate. At a data rate of 250 megasamples per second, you usually get about 80% usable bandwidth out of the sample rate. We'll be working at an 800 megahertz center frequency, and for software we'll be using Quick Transceiver by Quick Systems. After starting up Quick Transceiver, first we want to make sure that we're talking to the right type of eval board. We support numerous different combinations of eval boards and host boards, so here's the 9081 on a ZCU102. We're going to be talking to it over the network, and here's the IP address for it. Then we want to go and talk to the 9081 control. We're going to be transmitting out DAC 0 at 800 megahertz. We'll be receiving on ADC 0 at 800 megahertz. We're going to capture 50,000 acquired samples, and here's the 250 megasample per second mode that we're operating the chip in. We also want to make sure that we've got the right windows up so we can see the results that we're looking for. In this case, I'm using the acquired waveform, the acquired spectrum, the acquired spectrogram. That's all acquired data. The constellation, adaptive EQ coefficients, adaptive EQ response, and measured results. I think I'm also going to add the processing waveform. And then finally, want to make sure that we've got the right transmit file. So this is a linear frequency modulated LFM that starts 100 megahertz below the carrier, goes to 100 megahertz above the carrier with a pulse duration of 40 microseconds and a pulse start-to-start interval of 80 microseconds, so a 50% duty cycle. Alright, with everything set up, let's just go hit the start button and start the data flowing and being captured by the system. And I'm just going to stop it here for a second. We're just looking at the acquired data at this point, not doing any extra processing. So this is a chirp. In the time domain, it's just on for a while, off for a while, on for a while, off for a while. That's that 50% duty cycle. You can see on a spectrogram, which is a time frequency display, frequency is horizontal, time is vertical, and time starts at the bottom and plays out as we go up the plot here. You can see that we start here below the carrier frequency of 800 megahertz. We're 100 megahertz below, and we start our frequency chirp, and the frequency moves up in a positive direction during the time that the chirp plays out, and then it ends up at 100 megahertz above the carrier, and this total time here is the 40 microseconds, and then it's off for 40 microseconds, and then it's on for 40, and so forth. So let's now go turn on our arbitrary waveform equalization. We go up here to processing and arbitrary waveform equalization. First of all, we have to choose a waveform that is the waveform that we're playing so that we can compare what we get with the system compared with what it should have been ideally. In the processing, we'll have 33 taps, and the time accuracy is to the nearest sample. Now we go up here and hit start again, and what we see, if I stop it here, these are the tap coefficients that are being determined for the equalization filter, and here's the response of that equalization filter. You'll notice that the top of our chirp over here is not flat. I'll zoom in on that plot. You'll notice that it tends to go down maybe a little bit and then swing up at the higher frequency end of things. Our response of our system is not flat. It's got a little bit of character to it. And so what the adaptive equalization is trying to do is to come up with a filter that's going to compensate for the imperfections in our system. And in this case, we're only looking at the magnitude, but it would also be doing that in phase. This plot is displayed from minus 125 to plus 125 megahertz. The reality is the chirp is there just from minus 100 to plus 100. So we focus our attention from here to here on this plot. And you'll notice that it tends to roll down this edge, the higher frequency part of the thing. It rolls down. It actually initially rolls up and then it rolls down, because that's what it needs to do to compensate for the system response that we're trying to equalize away. Now that I have some tap coefficients that have been determined, I'm going to right click on the adaptive EQ coefficients plot, say save coefficients to a file, and we'll just save it as the complex FIR coefficients in a nice little text file format that we have. Then I'm going to go up here to receiver waveform processing, and I'm going to make sure that we apply those complex tap coefficients. And then for the moment, I'm just going to go back to the fixed spectrum analyzer mode, so no longer in the arbitrary equalization mode. All right. Run for a while and then let's stop. And you can see this is the time domain response after we have applied that complex FIR filter to the received data. And one of the things that you can note immediately is that this characteristic of the acquired data, which has this slight droop and then a flip up, has been totally flattened out. There's no droop left in the response up here. We've just flattened out the response. So at this point, the idea is that we have created a set of complex FIR tap coefficients using the chirp waveform across the entire usable bandwidth of the signal. Now we want to put that to work for us in doing some usable reduction in EVM. So let's go up here and call in a different kind of transmit file. And in this case, I'm going to use an 8PSK at 100 megasymbols a second, and just turn the signal on. And here we go. So we're transmitting an 8PSK waveform at 100 megasymbols per second. Carrier frequency is 800. And we have a carrier to noise ratio over here. Stop that plot from jumping. We have a carrier to noise ratio over here that is 57 dB. And our EVM that we're getting at this moment is 52 dB down, 53 dB down, something like that. If we go in here and we turn off those tap coefficients that are being applied as fixed equalization, you can see an immediate effect on the final symbols, and in fact the EVM is now something like 36 dB down. So again, if we go in here and we turn on those tap coefficients, doing some fixed equalization cleanup here, immediately the EVM improves significantly. Then if we want to, we could actually go in here and add on to the signal processing. We could add on some additional adaptive equalization just to do the final cleanups on here. And you can see if we do that, then the EVM gets very close to the carrier to noise ratio. But the response shows there's really not that much for the adaptive equalization to do at this point. Almost everything's being done by those coefficients that come from the chirp equalization that we did. For one final demonstration here, let's stop this. Let's go choose a 256 QAM kind of waveform just to run one other type of signal through this. And here's our 256 QAM. And I'm going to turn off adaptive equalization. It still has the fixed equalization that we have from the chirp tap coefficients. So there is a 256 QAM waveform that is using fixed equalization from those coefficients that we determined using the chirp type of waveform. And if we go in here and turn off the fixed equalization, then you can see the immediate effect on the final symbols there, and we're back to our EVM of maybe minus 36 dB, something like that. Alright, wrapping things up now. The previous video showed equalization using the received signal. One of the key points there is only the bandwidth of the signal can be equalized. You can only determine those tap coefficients in the region where the signal has appreciable power. In this video, we showed how to equalize the entire usable bandwidth of the receiver, and for that we used a different waveform, which is a chirp waveform in this case. Another reason to use a different type of signal than just your transmit-receive signal is that you may want a signal that has some better power characteristics. It might be that your transmit receive signal has some power characteristics that are causing a power amp to have some nonlinearity problems and things like that. But by using a constant envelope signal like a chirp, that might better operate with the amplifier in your system. That's it for this video. You can find out more information about Quick Transceiver by Quick Systems by visiting us on our website at quicksystems.com or by sending us an email at sales@quicksystems.com. Have a good day.